Hi everyone. In this video, I'm going to talk about direct delta distribution and the chrono delta function. These two distribution, we briefly mentioned that the other day. And it is a distributional function that is very handy when we deal with some physics question. I have no intention to actually prove it, but I just want to let you know a few properties of the function that you may find it handy in this class. Okay, so the first function I want to talk about is a delta function. So delta function x minus a, meaning that when this equal to a, when this whole thing is 0, so when x equal to a, then you will get an infinite, you will get a peak, like you'll get infinite. But if x is not a, you get 0. So you can imagine that this is a really good distribution function when we say we measure a position, right? When we measure a position, you see a dot. So like everything, like the entire wave function collapses into a dot. So this is the distribution to describe that. So I call it distribution. Some people also call it function. It is technically not really a function because it will explode at this point. So that's not a good function. It does not have a good behavior. So we sometimes call it generalized function. So just meaning, this guy depends on x. Okay, so this function is not only this. It also comes with the criteria that if you sum over all the entire space, it must be 1. So that makes, this even better because we know that once it collapses, it becomes, this function. But, the probability of finding my particle over the entire space should still be 1. So that makes this a good one to use when we talk about localized particle. So these two together defines the delta function. This delta function has a few properties. So first of all is that this delta function, I have a typo here. So this delta function, it also looks like this. So to prove that this looks like this, you will need to do some complex analysis, but you can roughly imagine that this guy is essentially, a vector on my unit circle, right? Okay, and this is like the angle. Okay. So because k can be anything, like k runs through negative infinity to infinite. So meaning like for different k, you're gonna have different vectors on this unit circle. Because there are like infinite of them. So you can imagine that eventually all these vectors are gonna cancel out. So it will be 0. But if x equal to a, then this term, your phase will be 1. Your phase will be 0. If your phase is 0, exponential I0 will give you 1. So you're essentially summing over all the k from negative infinite to infinite. So that will give you a non-zero value. And that will give you infinite actually. So when x equal to a, this integral will give me an infinite value. If it does not, it give me 0. The 1 over 2 pi here, it has to be explained by if you do the complex integral. Okay, so just kind of believe me on that and make sense of this physically. The second property is also somewhat self-explanatory. So you can see if I multiply a delta function with another function, then when I sum over all my x, okay, let's say when my x is 1, then this will be 0, right? Then that term will be 0. When x is 2, this term will still be 0. So f2 times delta times 0 is still 0. So which term will have non-zero value? Well, only the term where x equal to a. And when x equal to a, because once this become a, it's a number, you can take it out of your integral, then you can integrate this over, then that will give you 1. This is also another property. If you forget, you can look up on Wikipedia. Same here and same here. That's a derivative of the delta function. I'm not going to prove it per se, like in this class, unless necessary. But you can use them if you feel like you need to. Okay. Um, there is another distributional function that is very similar to delta function. Remember, that's when we talk about the discrete space and we say, oh, EI, EJ will equal to delta IJ because if they are the same, then it will be 1. And if they are different, then they will be 0. Okay, it's just meaning these two bases, they are orthogonal and they are normalized. Okay. This is normalized, by the way. Normalized meaning the amplitude, the strength of that vector is 1. Okay, so that's essentially the meaning of this. We don't really do any, it's not really a continuous space, so we cannot really do derivative or integral for that. It's just like an index. Like when you sum over all the ij, say ai, aj, right? And then that meaning when you sum it over, I must equal to j, only that term will survive. And all the other terms will be 0 because of delta function. Okay, so that's it. Nothing too much about this one. Yeah, I will try to, remind you of the properties when we actually need to use delta function, but I just want to put this at the back of your mind.